Hello everyone, my name is Tan Su. I'm a senior lecturer from the Mechanical Engineering Sciences, University of Surrey. It is a very pity that I'm not able to join you on site today. Therefore, I produced this pre-recorded lecture, which is entitled Final Scale Residual Stress Characterization in Laser-welded Eurofer97 steel for fusion plants. Europe has a very long history in fusion research. So back to 1970s, European laboratories joined forces to build the JET, which is currently located in Callan, Oxfordshire in the UK. The ITER is the largest international experiment, paving the way to the fusion energy. In 2007, an international project agreement has been signed to build ITER. In 2020, it was about ready for the assembly phase of the most powerful fusion device in the history of the mankind. So the demonstration power plants, which is called DEMON, will follow the ITER, paving the transition from the science-driven, lab-based experience to an industry-driven and technology-driven program. A key criterion for DEMON is the production of electricity, although not at the price and the quantities of the commercial power plants. Fusion energy is environmentally responsible because fusion does not emit any greenhouse gases. Deuterium can be found in the seawater with enough supplies to the last millions of years. Tritium can be generated from lithium extracted from the crust of the earth. It is also a very efficient fuel, where 60 kilograms of the fusion fuel can provide the same amount of the energy as 250,000 tons of petrol. So current fusion experiments were primarily designed to investigate plasma physics. However, DEMON must demonstrate the new technologies not only for controlling the high energy plasma, but for ensuring consistent and reliable operation by enabling the rapid assembly and maintenance. So ITER, which in Latin means the way, it will be the world's biggest experiment on the path to fusion energy. It will have millions of components, and all of this will be integrated into this biggest fusion device. The assembly of the device will be one of the most complex engineering operations. The test blanket modules are the test versions of the in-vessel components and will be tested in ITER in order to assess their technical potential. Eurofer97 is a newly developed reduced activation steel in Europe. It has been used as the structural materials for the test blanket module system, and these materials provide adequate resistance to the neutron irradiation, corrosion, and with acceptable resistance at a high temperature. Remote laser welding is one of the most promising techniques for assembly and maintenance of the in-vessel structures. This technique could give less distortion and enables the full penetration of the single-pass welds in thick sections. It has low heat inputs, leading to a narrow heat affected zone. However, this welding process still induces significant residual stresses of up to approximately 800 MPa inside welded Eurofer97, and changes the microstructure and the mechanical properties. So, what is residual stress? Residual stress is the stress that remains in the solid materials without external load. Welding process induces residual stress at different length scales. Most of the time, it is detrimental for engineering structural integrity. Therefore, evaluating the residual stress and exploring the connections with the mechanical properties and its interactions with the microstructure is crucial for components' reliability. Until now, we have many techniques to measure the residual stress, from destructive to non-destructive methods. As shown in this picture, each technique has its own spectral resolution and penetration. For example, EBSD and XRD, they both measure more surface residual stress at the micron scale. In contrast, the contour method measures the bulk residual stress in a destructive way. Here, in this work, we develop and apply the plasma focused ion beam DIC wrinkle method to measure the residual stress in the weldments. It provides time-resolved, multi-scale characterization of the residual stress. So, how does the P50IC method work? The incremental milling step using the PFIB releases the residual stress gradually as the milling depth increases, and the image during the milling process is acquired while the PFIB and SEM dual beam system. The digital image correlation DIC technique is then applied to visualize the strain relaxation that enables the residual stress calculation. The master curve fitting evaluates the macro-scale residual stress evaluation, and our approach in this work can also provide two-dimensional, time-resolved, micro-scale stress relaxation maps. We then applied the non-indentation method for the residual stress evaluation. So the wrinkle milled by the PFIB provides the residual stress-free reference areas to calculate the residual stress on the other locations. PFIB DIC method provides the location-dependent stress ratio, which is K, to transfer the equal biaxial residual stress to the non-equal biaxial. This is to overcome the main limitation of the non-indentation residual stress method, and also provides a cross-validation for both the PFIB DIC method and the non-indentation method. So, the grain morphology of the as-welded Eurofer97 steel is illustrated by the EBSD orientation map, from the base materials to the heat-affected zone areas to the fusion zone. And the microstructure can be seen in the SEM images at the bottom left. The grain size has been quantified, and the average size is about 11 micron in the fusion zone region, and 6 micron in the heat-affected zone region, and 7 micron in the base materials region. And the macroscopic residual stress distribution is then characterized by the PFIB DIC wrinkle method in two directions, in the X direction as well as in the Y direction. So the time-resolved macroscopic strain relief curves and the maps of the strain relaxation are shown as example on the right-hand side of the page. From the strain relaxation mapped at the right bottom, we can see that the residual strain relief gradually during the milling processes, and the localized accumulation of the micron-scale strain relaxation can be an indicator of the crack initiation and the failure. Looking at the color bar, the microscale strain could be significantly larger compared to the macroscale residual strain. So combined with the EBSD orientation map, we could correlate the microstructure and the residual strain at the final step of the time we resolve the measurements. The overlaid EBSD map enabled the visualization of the crystallographic orientation, and this red outline reveals the position for the digital image correlation markers. The displacement maps in the middle disclose the corresponding deformation of the wrinkles because of the residual stress relief. The residual strain can be further derived from the displacement map. On the right, it shows anisotropic effects on the residual strain. The cubes in the figure represents the grains in the different orientations. This also implies that the grains at a different crystallographic texture show the similar deformation behavior during the strain relief. In this case, the microscale residual stress significantly affects the residual stress distribution. On the left, it is the distribution of the two principal residual stress components derived from the P50IC method, which you can see the peaks values at interface. On the right, it is the distribution of the two principal residual stress components measured using the non-indentation, where the equal biaxial residual stress was transformed to the non-equal biaxial residual stress by the location-dependent stress ratio K. Both figures display similar trends, although the peak values at the interface show some level of disagreement regarding the magnitudes. The sharp microstructure and the residual stress gradients usually exist in these transition regions, which indicates that the location-dependent stress-free reference at a high resolution is desirable to improve the quality of the non-indentation residual stress measurements. We also evaluate the local hardness, and the local hardness values depend on the residual stress and the microstructure, for example, the grain size, the precipitate size, etc. Our nano-indentation methods enable the quantitative evaluation of the microstructure and the residual stress effect on the hardness. We produce those residual stress-free wrinkles. We then apply the non-indentation on top of the wrinkles. By doing so, the hardness values on the wrinkles will only depend on the microstructure. If we have a close inspection of the figures, we could find that although the total hardening is the same between the fusion zone and the heat-affected zone areas, the origin of the hardening effect is really different. The microstructure hardening is the dominant mechanism for the weldment. In conclusion, our analysis of microstructure and the residual stress distribution in laser-welded Eurofer97 steel using a number of advanced microscopy techniques, for example EBSD, P50IC, and nano-indentation, really offers new tools for evaluating the multiscale residual stress. Our approach has provided insight into the critical engineering challenge of the laser-welded Eurofer97 steel. The residual stress contributes around 25% to the hardening and softening in the fusion zone and the heat-affected zone. Our method can also be applied for many other similar metal joints, for example the in-vessel fusion components and even more complex material system. Finally, I would like to thank all the collaborators and the founders to make this work happen. I also put up the link to our recent published paper in Science Advances, and if you have any questions, please feel free to contact me. Thank you very much again for your attention.